Okay, hi Year 11. Just about finished this topic on permutations and combinations with combinatorics. There's two sections to go, up to the second last one, and it's arrangements in a circle. This will match up with 14G in our textbook. So when we're arranging people in a circle as opposed to in a line, it happens a little bit differently, and we're fixing that first person that sits in the circle. So let's have a look at a couple of diagrams before we look at the notes below. So I've moved over into the OneNote where I've popped some stuff from the textbook, and I've got 5 circles below. I'm just going to read the notes above it and we'll talk about what's happening in those circles. Arrangements in a circle or around a round table are complicated by the fact that two arrangements are regarded as equivalent if one can be rotated to produce the other. For example, all the 5 round tables below, and they seat King Arthur is A, Queen Guinevere is G, Sir Lancelot L, Sir Bors is B, and Sir Percival is P. These are all regarded the same. As if we have a look at what's happened here, we're moving our people clockwise around the circle. If I see Arthur first, then going clockwise, I see Guinevere, Lancelot, Bors, and Percival. I actually have the same circle as if Arthur chooses the seat next to him, next to where he was on that first spot. So if Arthur chose this second spot here, and then I sit Guinevere, Lancelot, Bors, and Percival, I've got the same circle with the people in the same order. I've just basically rotated that circle around. So we would regard these two circles in these sorts of questions as identical. Likewise, if Arthur chose the third seat around, his spot's fixed. And then if we put these other people around clockwise like that, they'd also be regarded as the same. So we need to, I guess, understand that that is the case, and that will help us have a look at the notes. So let's jump back to those now. Okay, so the top of our notes say that when working out the number of ways of arranging people in a circle, it's n-1 factorial ways. So let's have a look at what that means in relation to our King Arthur question that we had a look at. So here's my seated table of 5 seats, and I've got 5 dashes there for those. And I've just got Arthur to pick a spot. So he's picked his first spot here. So we are saying that when he picks that, he's fixed, and there's basically one way he's going to choose it, because wherever he sits, whether it be that spot or the other 4 spots, it's up to him, and that's not taken into account. So his first spot is fixed that he chooses, and then our next person comes in. It's probably Guinevere, and in this case, we are letting her choose where she wants to sit. So she's got 4 options to sit from, okay? She can't sit where Arthur sat because his spot's gone, but there's 4 spots to pick. The next person comes in, which is probably Lancelot. He's got 3 options to sit at. The next person has 2. The last person has 1. So if we've got 5 people, we've got 4 factorial ways in order to seat them around a table. So that's where our n-1 factorial came from. 5 people is n, take off 1, and that's the rule without restrictions around our table. So likewise, 8 people in a circle could be seated 7 factorial ways. 10 people could be seated 9 factorial ways. And this, we say that this eliminates the rotation of the same seating around the table. So that's how we get around those 5 knights of the round table scenarios all being identical. Let's have a look at the question below. So we've got John, we've got Mary, Bob, Albert, and George. So we've got 5 people. They're going to a dinner party. The table is round. We want to find the number of ways that they can be seated around that table. Now, the first one's fairly straightforward. A is saying there are no restrictions. So when there's no restrictions, that is when we're looking at this n-1 factorial. In that case, one person takes the first seat. We don't know who it is. We'll say it's John, perhaps. He sits down. He sits wherever he wants. And so where everyone else sits is dependent on where he sits. So the other 4 people can take a spot in n-1 or 4 factorial ways. So there are 24 ways that they can sit around a round table without any restrictions. So that's the easiest scenario. Let's have a look at what we go for the others. Now, the rules that we're going to use for the next lot are going to take into account some of the rules that we've already done in our permutations and combinations questions in our previous exercises. So part B says there's 5 of them at the table's round, but John and Mary want to sit together. Now, like we've done before, I suggest we draw a diagram because visually That's going to make our life a lot easier with these. So I've got 1, 2, 3, 4, 5 spots. John and Mary need to sit together. So we've got John, we've got Mary. They're sitting together. They're going to take 2 seats. But we don't know if, say for example, if John takes this seat up here. I don't know if you can see my pen there. If John takes that seat there, then Mary's going to either take that seat there or that seat there. Okay, so we don't know if Mary's going to be to the left of John or to the right of John. So there's basically 2 ways that they can take their positions. So we can write it as 2 ways or 2 factorial ways. Now, if they've taken their positions, how many other people are left? We've got 3 people left in there. So there's 2 spots that are gone. So basically you can cross out John and Mary up the top there. And we've got Bob. He's going to come in. And how many ways can Bob make his positions? He's got 3 options to sit down at. Because John and Mary have taken their spots, he's only got 2 choices. Bob has 3. Albert's got 2. And George, well, he doesn't have any choices. He gets to sit at the last remaining seat. So our answer there to how many ways can they make those seating arrangements happen is John and Mary have got 2 ways that they can sit. And everyone else has got 3 times 2 times 1 or 3 factorial ways in which to sit. And that's 12 different ways. Now, that's the way I like to think about it. You can also think of it as grouping John and Mary together. So we've got, instead of having 5 people, we've got 1, 2, 3, we've got 4 groups. We can think of it as. In this case, n would be 4. And so we'd have a seating arrangement of n minus 1, which is 4 minus 1 or 3 factorial ways. But we need to take into account that John and Mary have 2 options themselves. So same maths, just a little bit different thinking if you like to think that way. And I know we all in this class think of slightly different. So we want to try and have a look at all options. Okay, part C. What can we do if John and Mary want to sit apart? Okay, so if they want to sit apart, that means they cannot sit together. So there's a couple of ways we can look at C. When John and Mary want to sit apart, like I said, it's total number of ways that they could sit minus the number of ways they can sit together. Because if you think back to how you think of probability, sitting together and sitting apart, they're all your options. So if we look at total ways and take away the ways they sit together, that's going to be equal to the ways they sit apart. And the reason I'm looking at doing it this way is we've already done A and B, so it makes it a little bit simpler. So the total ways is 24. Take away the 12 ways that they sit together, gives us 12 ways that they can sit apart. But what if we were asked this question and we hadn't already worked out what the total ways were, or if we hadn't worked out the ways that they do sit together? We might as well just work out the ways that they can sit apart. So let's have a look at that. So I've redrawn our little round table here, and I've written everyone's initials to the side. So we've got John and Mary and Bob and, I can't remember what our last 2 names were. Let's have a look who they were. Albert and George, that's who they were. Okay, so they need to sit apart. So John's going to go in and take his seat. And there's one option in terms of he's fixed. So he's got to pick that spot, and that's not going to take into our calculation. So let's just say, for example, John picked up here. Now, if they need to sit apart, that means Mary comes in. She can't sit here and she can't sit here. So Mary's only got 2 options of seats that she can take. Okay. So she's got 2. So she's picked one of these 2 there. So say she's picked this one over here on the left. Bob comes in. Bob's got 3 choices then that he can pick from. Albert's got 2 and George has got 1. So if we times those together, we get 12 ways as well. So that's just another thought to think that, yep, there's often multiple ways to work out these questions, and we want to know how to do all of those ways. Okay, part D, a little bit more tricky. Part D says, George wants to sit between Albert and Mary. Let's draw ourselves another diagram. So what we want to do is, I might just reorganize these letters over to the side here. So George wants to sit between Mary and Albert. Okay. So we're going to group those guys together. And we've also got a group of the last two people, Bob and John. Or not a group, they're going to be separate, sorry. So we've got to think about what happens. And this is similar to the standing in a line question that we did before earlier on in this topic. So if we've got these three together, Albert, George and Mary, how many ways could they sit? So George has got to be in the middle. So Albert could be on the left of George, Mary to the right, or we could have it the other way around. We could have Mary, George and Albert, and they would take up 3 positions in this table. Okay, but we've got to group them together. So maybe they're grouped into that section there. But there's 2 possible ways, or 2 factorial ways that they can move around. So then we're going to think of it as, well, we've actually got 3 groups within there now, haven't we? We've got 1, we've got 2, and we've got 3. So how many ways can we then arrange those 3 groups around the table? Well, it's going to be n minus 1 factorial ways. So that's going to be 2 factorial ways. So all up, we've got 2 ways to group George between Albert and Mary, and then we've got 2 factorial ways in which the whole bundle of them, or the 3 groups, can sit around there, which is 4. And that's our answer for that one. Okay, let's have a look at our next example. 4 boys and 4 girls sit around a table. How many ways can this be done if there are no restrictions? Okay, if there are no restrictions, we've got 8 people around that table. We would have n minus 1 factorial ways, which would be 7 factorial ways, which is equal to 5,040. Then we're going to have a look at what happens if the boys sit alternate to the girls. So you may want to draw yourself a little diagram for this again. So let's do that. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so because we've got 4 boys and 4 girls, so because they're equal, it's not going to really matter if we start with the boys or start with the girls. It will be exactly the same. If we had, say, 4 boys and 3 girls, and they were different numbers, it would make a little bit of a difference with our calculations. So let's say we've got, sit the boys first. Let's do that. Only because they're first in the question. So the first boy is going to go and sit down somewhere in that allocation of seats in that circle. So I'm just going to write it down like that. So we've got the first boy, second, the third, the fourth. And maybe you can picture this easy and you don't need to go into this much detail. But the first boy is going to sit down. He's going to sit and we're going to fix his spot. So he's got basically one position that is going to be fixed for him. The second boy, and let's just say he sat up there. The second boy then can either sit here, here, or here, because we're looking at alternate ways. So we're going to, I guess, assume that those other chairs in there don't exist. So that second boy can sit in n minus 1 factorial ways. So the second boy's got 3 ways to choose. Then we've got 2 and then we've got 1. So we've basically got 3 factorial ways that the boys can sit. Then we're going to sit the girls. Now this is where it's a little bit different. Now we're not fixing the position of the girls because we've already got seats in there. They don't have a choice on, or they don't, sorry, they do have a choice. They don't need to fix their first position. So the first girl has got, and we'll call this the girls ones in here, 2, 3, 4. The first girl's got 4 spots in which that she can choose to sit. The second girl's got 3 ways. The third girl's got 2 choices, and that last girl just sits in that last spot. So there's 4 factorial ways that the girls can sit. So all up, in seating them, we've got 3 factorial times 4 factorial ways, which is 144 ways. Part C, we want the boys to sit together. So let's draw ourselves a table again. So I've drawn my table over here, and in order to populate that table, the 4 boys need to sit together, and the 4 girls we're going to think of as separately. Although, in essence, they're really going to be sitting together because of the ways the boys sit together. So we still think of the boys that sit in there as 4 individual boys. You know, someone's got, you know, straight hair, curly hair, red hair, brown hair. They all look different. So within those 4 boys, they can sit 4 factorial different ways. Okay, so the first one picks his spot within his 4. He's got 4 choices. The second boy's got 3. The third one's got 2 and the last one's got 1. But around that circle, we're going to think of them as 1, 2, 3, 4, 5. We're going to think of it as n equals 5 around the table. Okay, because we've grouped the boys together. So in grouping those boys together, we've got n minus 1 or 4 factorial ways around the table. But we've also got within that group of boys 4 factorial ways in which to group the boys. So the solution is going to be 4 factorial times 4 factorial, which gives us 576 ways.